Okay folks, so we're back looking at some examples of double integration. Okay, so here we go. Sketch the rectangular, I'll just make sure I covered everything here. Yeah. Sketch the rectangular lamina with these vertices. Suppose the density of the point is given by this. Assuming SI units, find the mass of the lamina. Okay, so this, it'll really be in the examples now that we get some kind of figure out what's going. Now just be very careful not to mix up your x and y here. So yeah, there's actually just a bit confusing bit here. So this should say x between 0 and 2. Okay, because let's look at the 4 points. We got 0, 0. We've got 2 along the x, 0 along the y, 2 along the x, 3 along the y, which I haven't done to scale, 0 along the x, 3 along the y. So this is our rectangular lamina. So it's a two-dimensional shape, not just the outsides. Okay, so what we're going to do now is we're going to add up, essentially, over this lamina, rho xy, which is 2x squared y, times dA. Now dA is a little bit of area, and it's equal to a little bit of x by a little bit of y. So essentially this is what we're doing. Now we're adding up over infinitely many points. So we're adding up over every internal point in this, which is infinitely many. And because of the dx and the dy, these things are infinitely small. So that means that we're ending up with integrals. Okay. Now how we add up over all these points is we fix a constant x between 0 and 2. And we imagine a strip, a very, very narrow strip. And you're supposed to imagine that the width of this is dx. So constant width of this strip, width dx. So dx is a constant, and then x is just some number between 0 and 2. Okay, so we're going to find the contribution to the sum from the strip at x, and the strip goes from y equal to, we're adding up from y equal to 0. Now you might say, oh, I don't really see how we get from, oh, okay, what you say, oh, you said adding up all the small things, infinitely many, infinitely small things is integration, but how do you get from there to integrating from y equal to 0 up to y equal to 3? Well, you're probably just going to have to take my word on that. It would probably take too long to fix everything that I did. I was just trying to give you a rough idea of what integration is. So here we said, noting dA is equal to dx dy, and x and dx are constant along a strip, the mass of the strip. So we're going to find the mass of this strip. So the mass of the strip is found by adding up, which is now integrating because we're adding up infinitely many small things. We'll write y equal to 0 to y equal to 3, and we're adding up density per unit area times area. So the density was given to us in the question as 2x squared y dx dy. Okay, now what we're going to do is everything that's a constant we're going to pull out. So if you look at what we're doing, so this is a little bit like partial differentiation. Along this strip, only y is changing. So this is constant, and this is constant. Everything else stays inside the integral. So take out the constant 2x squared dx. I'm left with an integral from 0 to 3 y dy. Now in terms of the integrals that I expect you to do, they're not going to be that difficult. Okay, they're all pretty much going to be in the tables. Now this particular one, how do you integrate y? Well, recognize that y is y to the power of 1. And how do you antidifferentiate a power? You add 1 to the power, divide by the new power. So you're going to have 2x squared dx, which you could, by the way, if you're being a bit lazy, you could say, oh, define this to be equal to alpha of x or something like that. So you wouldn't have to write it every time, but we won't do that. So it's a constant here, but it won't be a constant in a second. So antiderivative of y to the 1 is y squared over 2. and now we're doing top limit minus bottom limit. So this is equal to 2x squared dx. And now we're getting, so substitute in the top limit, 3 squared over 2 minus substitute in the bottom limit, 0 squared over 2. Now there's a small comment here about inputting a 0 limit. Often you'll see that when we put in a 0, we get a 0. So here, for example, you put in a 0, you get 0 squared over 2, which is 0. But if there's like a cost term or an exponential term, e to the 0 and cost of 0 are 1, so be careful. So what we get now is we have the 2 by 3 squared over 2, which is 2 by 9 over 2, that's 9. So that's 9x squared dx. And that's the mass of the strip of constant width dx. Well, you can think of it as the mass of the strip of constant width dx at x. And notice that as x gets bigger, the mass gets bigger. And this, because of the dx, this is it's an infinitely thin strip. It has an infinitely small mass. But what we're going to do now is we're going to add up all the strips. Strip at x equal to 0 all the way up to x equal to 2. So we're adding up the mass of all of these. So the mass of the lamina is now found by adding up from x equal to 0, x equal to 2, the mass of the strip. Now there's infinitely many strips. They go from x equal to 0 to x equal to 2. And at, say, x, the mass of the strip is 9x squared dx. So now we're adding up the masses of the strips. And if you add up all, the strips make up the lamina. So here what we might do is, if we're going to keep maybe doing this crack about fixing constants, here 9 is a constant. So fix the 9, and you've got the limit from 0 to 2 x squared dx. And as I said, the actual integration that I give you will not be too difficult. And in fact, I've already given you the assignment, so you can see it's not going to be too difficult. So antiderivative of x squared, add 1 to the power, divide by the new power, 0 to 2. And again, top limit minus bottom limit. So I get 9 times 2 cubed over 3 minus 0 cubed over 3. And 8 over 3 times 9 will be, fairly sure that will be 3 times 8, which is 24. Now we should be looking for units, assuming SI units. What's the SI unit of mass is kilograms. So there you go. Not too bad. Not too bad so far. So you're just adding up over a two-dimensional shape. First add up, find the mass of a strip, and then add up all the masses of all the strips, but there's infinitely many of them, and because they're infinitely thin, the mass of each of them is infinitely many small, so you're getting an integral. Hopefully you kind of get used to this idea. Okay, I think we're going to do another example here. Sketch the triangular region with these vertices. Okay, now be very careful because it's kind of a stupid thing to get wrong. So 0, 0, 4, 0, and 4, 4. Okay. And what we're trying to do is find the centroid of this. Okay. It'll be using integration. Okay. So what we're going to do is, this time we're not thinking about finding the mass of something. We're thinking of adding up over this triangle. Okay, so I could draw this, yeah. Okay, so we're adding up over this triangle. So we're adding up x by dA over the triangle and y by dA. I think we're going to find the x one first. Now, the a there is the area. We can just find the area, half the base by the height. That's 8. That's no problem. So what we're going to do is we're going to fix a value of x between 0 and 4. And we're going to add up from x equal to 0. And then the question is up to what? Sorry, y equal to 0 here. And then the question is y equal to what? Now, what the y coordinate is actually depends on the x coordinate. Like if x is 0, y is 0, and x is 4, y is 4. we need to be a little bit careful here. So really what we need to recognize is two things. The height of y is a line. So the y coordinate, like on the triangle, lies on a line. And let's say it's y equal to mx plus c. Now it's quite an easy y equal to mx plus c because we have the picture drawn. So what's the slope? Rise over run. So the rise as you go from 0, 0 to 4, 4 is, it goes from, the y coordinate rises from 0 to 4, which is 4. And the x coordinate runs from 0 to 4 as well. 4 over 4, which is going to be equal to 1. And then the constant is where it cuts the y-axis, and sure, it cuts the y-axis at 0. So you get that the y coordinate is actually equal to the x coordinate. So at some fixed x between 0 and 4, the y coordinate above it is equal to x. So we're integrating from y equal to 0 to y equal to x. Now what we're adding up is x. So let's go at that. Now these are, so this is a fixed x, constant x. Let's see. So again, along this strip, the x and the dx are constant. So we're going to take those out. So x dx, and we're integrating dy from 0 to x. Now, there's different ways to deal with this integral of dy. I think I have two ways, I think. So the first way is to say that the antiderivative of dy is the antiderivative of 1 dy, and what do you differentiate to end up with 1? If you're differentiating in respect to y, well, of course it's y. So this antiderivative of dy is y. That's one way of doing it. The other way to do it is think about adding up dy. This is a little bit messy here, but it'll work. So this is like adding up little bits of y, and when you add up little bits of y, you get y. So however way you spin it, this thing here, the antiderivative when there's, well, really it's 1, I suppose, to be is more accurate, because it's like x by 1 by dx dy. So whatever way you want to spin it anyway, you'll get x dx, and then the antiderivative of 1 is y. X. And now we do top limit minus bottom limit. So this is equal to x dx, and now do top limit minus bottom limit. So y equal to x minus y equal to 0. So you get x by dx by x. So you can do the x by the x is x squared dx. So you can probably see that as the x value is bigger, like you're just adding up the x coordinate here by dx dy, and you can see that there's more to add up the bigger x gets, which is basically the story. Okay, so this is the contribution to the sum from the strip at x. Now we're trying to add up x over the entire, x dx dy over the entire thing. So we need to add up the contributions from x equal to 0 up to x equal to 4. So this would be called add up over the triangle x dx dy is equal to add up the contributions from the strips at x, from x equal to 0 up to x equal to 4. What's the contribution to the sum? At the strip at x, we just calculated was x squared dx. Okay, now how do we calculate integrals? Well, we anti-differentiate. What's the antiderivative of x squared? X cubed over 3. And we're going from 0 to 4. So this is equal to, substitute x equal to 4 cubed over 3, minus substitute x equal to 0 cubed over 3. And that's 64 cubed is 64 divided by 3. And if you look at the formula up above, it says that the x coordinate of the centroid is that 64 over 3 divided by 8, and we get 8/3. So 8/3 is, it's kind of just shy of 3. So roughly we're talking something like this. Now you probably have learned in other modules how to find the centroid of a triangle, and I suppose what I'm telling you is where do those formulas come from, and this should end up being quite familiar. So now we'll do the other sum, which is to add up y. So we'll go back to the same strip, and we're going to add up y dx dy from y equal to 0 to y equal to x, same thing. So let's just write that we're adding up y d, well actually we're just adding up a little bit of it. So the contribution to the sum, so I could say adding up over the strip at x, and what are we adding up? Y dA is the same as adding up from y equal to 0 up to y equal to x, y, and dA is dx by dy. Now this time the only constant is dx, because y is changing from 0 up to, it's going from 0 up to the line. So we can take out that constant dx, and we're left with an integral from 0 to x, y dy. Now it's what do you differentiate to end up with y? Well, if you write it as y to the 1, you can say, okay, add 1 to the power and divide by the new power. So you get dx, and the antiderivative of y to the 1 is y squared over 2 from 0 to x. And similar story to above, I think we have space here. So you get dx, substitute top limit minus bottom limit. So y equal to x, giving you x squared over 2, minus y equal to 0, giving you 0 squared over 2. So what we get here is a half x squared, because dividing by 2 is multiplying by a half, dx. So if you're adding up y dA over a strip, the bigger x is, the bigger that sum is going to be. And there's two reasons, I mean, why it gets bigger. So as x gets bigger, essentially you're adding up over a longer strip, and the y coordinate is getting bigger. I think that's about all I can say there. Yeah. Okay, so now what we're going to do is add up from each strip at x equals 0 to x equals 4. So we get integral over the triangle y dx dy is equal to, add up from x equal to 0 to x equal to 4, the contribution to the sum from a strip, which is a half x squared dx. Now to be consistent, we might take out the constant of a half there. There's really no need. You can just write down half x cubed over 6, but we'll keep doing it. So fix the constant a half. We're integrating from 0 to 4 x squared dx. So as usual, add 1 to the power, divide by the new power. So instead of x squared, the antiderivative x cubed over 3. Top limit minus bottom limit. So we get half. So the top limit, x equal to 4 cubed over 3, minus bottom limit, 0 cubed over 3. And bang that into the calculator or whatever, you get 64 over 6, which is equal to 32 over 3. And then if you look at the formula at the top of the page, you'll see that the y coordinate of centroid is that integral divided by the area, which is 8. So we do 64 over 6 divided by 8, we get 4/3. That's the y coordinate of the centroid. So find 4/3, well, that'll be kind of a little bit bigger than 1. So you think it's something like this. And so you get the centroid there. And that, obviously the picture isn't to scale, but that doesn't look too bad. Okay, and that'll be the point where there'll be no internal torques. Right, so I think, have we got any more examples? Yeah, we're going to do another example here. Sketch the triangular region with these vertices. Find the second moment of area of this region about the x-axis. Now again, you have to use the integration. You can't use a formula. If you want to check your answers, that's fair enough. But we're just kind of giving you the theory of like where do these formulas come from, and if you're ever faced with some shape that isn't in the tables, you'll be able to deal with it, theoretically anyway. So 0, 0, I won't go to scale here. 1 along the x, 0 along the y, and 0 along the x, 2 along the y. So just remember, it's not just the triangle, it's the whole two-dimensional triangular region. Now what we might expect to see here, when is the contribution to the sum going to be big? So we're going to fix an x between 0 and 1. Now we're adding up y squared dx dy over a strip. Obviously when x gets close to 1, there's nothing to add up and the y's don't get big. Whereas when we go closer to x equal to 0, we're adding up more stuff and the y is getting bigger, so the y squared is getting bigger. So we should expect that whatever we get will be biggest at x close to 0. Now I know this one is a little bit nasty, and I will give some hints for those of you who are good at integration, because there's some very good students in this class, but I'll be doing it a different way. Okay, so the question is, we're going to add up, this is y equal to 0. The question is, what is the y coordinate here? Now once again, you have to recognize that this, whatever it is, lies on a line. This line that goes from y equal to 2 to x equal to 1. That's the line I'm talking about. So it's y equal to m. Now you have to be careful here. You can make a sign error, and I think if you make the sign error, your answer actually, well, if it's a centroid, if your answer is like the triangle is what's called a convex shape, which means its centroid is in the interior. You can have things that are like toilet seats, that the centroid isn't in the interior, or kind of like U shapes, similar story. But this is actually just calculating a number. So what I'm saying is you have to get the slope right. Now, you might say, like I'm basically telling you here, this slope is negative, okay? Now you might say, well, if you walk from the 1 to the 2, sure, it is uphill, so it's a positive slope. You have to pick something to be positive and something to be negative, and kind of really what we say is if it's going okay, you go from x equal to 1 to y equal to 2, you're going backwards. The x is getting smaller, so y is getting big but x is getting smaller, and so you have a mix of one getting big, one getting small. So basically, I'm kind of making a mess of this, aren't I? So you got two options: use your y2 minus y1, or you do rise over run and understand that this is negative. But actually, it shouldn't matter. So say you go from 1 to 2, then you say, oh, my rise is plus 2. And I go, well, your x is actually, your run is negative because you're going from 1 to 0. So you get minus 2. Or else you go from 2 to 1 and you say, well, the rise, it actually goes down from y equal to 2 to y equal to 0. So the rise is minus 2. And then you say the run is plus 1. But of course, these are both equal to minus 2. Mx plus c, where it cuts is 2. Now for reasons, it's going to be easier to write this as 2 minus 2x. Okay, rather than what we had. So we're adding from y equal to 0 to y equal to 2 minus 2x. Okay. So to find the second moment of area, we need to integrate y squared dA over the entire triangle. First, we fix the x between 0 and 1 and add up the contribution. So actually, we're going to find the second moment of area of the strip. And because the strip is infinitely thin, it's going to actually be infinitely small because it's going to be multiplied by dx. So this is to add up from y equal to 0 to y equal to 2 minus 2x. What are we adding up? Y squared dx dy. Now just for space reasons, I'm not going to write the next line that I normally write, just because there's no space. Fix the constant dx, so we're just going to fix that now. And then we're going to anti-differentiate y squared with respect to y. So as usual, add 1 to the power, divide by the new power. And we're going from 0 to 2 minus 2x. Now when we substitute in 0, we'll get, well, let's show it here. So get dx So put y equal to 2 minus 2x. So you got 2 minus 2x. You'll need the brackets here. Cubed over 3 minus 0 cubed over 3. So what I'm going to say here is that this is, well, it doesn't really matter. Now we are going to integrate that on the next page, okay? Because we need to add, this is the second moment of area of a strip. We need to add up the second moments of area of the strips from x equal to 0 up to x equal to 1. We need to integrate this thing here. Now I will say that there is a trick with this. So the 3 here is dividing by 3 is a third. So basically what we're looking at, we're hoping to integrate 1/3 2 minus 2x cubed dx. So this is what we're going to be doing on the next page. So you don't have a product rule for integration. So so you can't do it directly from any tables or anything like that. Now I would have said, oh, you do manipulation, and the manipulation is what we're going to do here, which is to say we're going to multiply out the 2 minus 2x and turn it into a sum and then integrate term by term. But if you were quite good at differentiation, it would probably be easier to do a substitution. Now, if you were, so you could do u equal to 2 minus 2x. And that should end up with, if I'm careful, you should end up with minus 1/6 u cubed du. And then, that's u to the minus 1/6 u to the 4, and then you put the u back in terms of x, and you do your x equal to your top limit minus your bottom limit. So there is that option, but I think while it might be a little bit longer, it's better just to multiply out the 2 minus 2x. So we're going to multiply out 2 minus 2x. I actually do notice another trick, just for the first time there. So you could write 2 minus 2x cubed as 2 times 1 minus x, all to be cubed, which is 8 times 1 minus x, all to be cubed. And then you can just multiply out 1 minus x, all to be cubed. It's a little bit easier than what we're about to do. So in any case, we need to do the antiderivative up in the top left-hand corner. And the easiest, well, technically easiest, not shortest thing to do is multiply out 2 minus 2x, all cubed. So to multiply out 2 minus 2x cubed, I'll first do 2 minus 2x by 2 minus 2x. So I get 2 by 2 is 4. 2 by minus 2x is minus 4x. Minus 2x by 2 is minus 4x. And minus 2x by minus 2x is plus 4x squared, which I can tidy up slightly by saying it's 4 minus 8x plus 4x squared. Now, if I want to find 2 minus 2x to be cubed, I need to multiply that by 2 minus 2x. And you can see it would have been slightly easier if we took out the common factor of 2 cubed. So we get here 2 by 4, which is 8, 2 by minus 8x, which is minus 16x, 2 by 4x squared, which is 8x squared, minus 2x by 4, which is minus 8x, minus 2x by minus 8x, the minus 2 by minus 8 gives us plus 16, and the x by x gives us x squared. And finally, minus 2x by 4x squared is minus 2 by 4 gives us 8, and x by x squared gives us x cubed. And we can add together the x's and the x squared. So we get 8 minus 24x plus 24x squared minus 8x cubed. There's something as well called a binomial theorem that can possibly make that a little bit easier. Okay, so we need to integrate that divided by 3 dx on the next page, added up from x equal to 0 to x equal to 1. So the second moment of area, hopefully I can remember that now, of the triangle is equal to integrate from 0 to 1, 2 minus 2x all cubed, which we just calculated to be 8 minus 24x plus 24x squared minus 8x cubed. So that's 2 minus 2x cubed, all divided by 3, which is no problem because that's just a constant 1/3 dx. So we'll take out the constant 1/3, we'll fix that, and now let's anti-differentiate the 8 minus 24x plus 24x squared minus 8x cubed term by term. Now, what do you differentiate to end up with 8? 8x. Okay? Yeah, because that's what anti-differentiate. So if you differentiate 8x, you get 8. So if you anti-differentiate 8, you get 8x. The next one, we're going to fix the minus 24. And the antiderivative of x is x squared over 2. Plus fix the next 24, and the antiderivative of x squared is x cubed over 3. And then fix the minus 8, and the antiderivative of x cubed is x to the 4 over 4. And we're adding this up from 0 to 1. So we're going to substitute in top limit minus substitute in bottom limit. So we get 1/3. So substitute in x equal to 1. 8 by 1. Now I'm going to do the minus 24 divided by 2 is minus 12, kind of thing you should be familiar with. Remember, lots of stuff like that in the beams. Times x squared is 1 squared. Plus 24 over 3 is 8. Times x cubed is 1 cubed. Minus 8 over 4 is 2 times x to the 4, which is 1 to the 4. Minus substitute in the 0. So you get 8 by 0, 0. Minus 24 over 2 by 0 squared, which is 0. Plus 24 over 3 by 0 cubed, which is 0. Minus 8 over 4 by 0 to the 4, which is 0. So all that's going to be 0. And then we just go into the calculator with this. So I'm going to do 8 minus 12 plus 8 minus 2. And I get 2 by 1/3 is 2/3. Now there's no units. So I won't write down the units of SI units of second moment of area, but I will just say what they are here. So the SI units of second moment of area, so it's y squared, which is meter squared, and then dA, which is the dx by the dy, is meter by meter. So it's actually meter to the power of 4. Now you might use slightly different units somewhere. Now there's one thing to say, it's very important that this thing comes out to be positive, because what you're doing is you're adding up y squared, which is positive, times an area which is positive. This has to be positive. If you get out something negative, you've made a mistake. Okay, so that's that.